Hi, everyone. Welcome. It's 7th of July, 2025, and it is On Lab Script Reading Group. Just as a reminder, we do have a Notion page and a mail list, so you can find the Notion page and a mail list inside of that in the invitation that you got or on Lab's Notion site. The seminar is going to last for 1 hour, and questions during the talk are very welcome and encouraged. Obviously, when the speaker is speaking, you should raise your hand or do it when the speaker is suggesting you to ask a question. Today, I'm very happy to have Dimitris Kounalis, who is a postdoctoral researcher at UC Berkeley, hosted by Sanjam Garg, working general in cryptography. Before, Dimitris was a PhD at MDIA, Software Institute Madrid, where he got his PhD in 2024, working with Dario Fiore. Today, Dimitris will be giving a talk on Jigsaw, private smart contract protocol with both on-chain and off-chain privacy. The work was pre-published just recently as far as in June, and I had a chance to attend the earlier presentation at the Eurocrypt affiliated workshop earlier in May, which was very good. So I'm always excited to see concrete solutions that unite privacy in the context of collaborative execution, which is a very important problem, I think, and it's really hard to solve practically. So that being said, please welcome Dimitris Kounalis.
Okay, hi everyone, and thanks a lot, Misa, for the introduction and of course for the invitation. So I'm actually very happy to give this talk for ON Labs. I think that it's kind of a work that is more in the practical side. So I mean, I think all of us would be very happy to see this work. More than happy to see this work. More happy to see this work like somehow used than actually published. So it's like something that we believe that has the potential to be practical, to be deployed. So it's I guess it's a very suitable audience for this work. So yeah, it's Jigsaw. We introduced something that we call Doubly Private Smart Contracts. As Misa said, it's gonna be about a new notion of privacy in smart contracts that we call off-chain privacy. It's a joint work with Sanjam, Arushi, and Rohit. These are more or less these are people, the people from the group that I am now as a postdoc, and people that used to be, and in general, close to the group that I am. Yeah, and yeah, let me start with the outline. So for this talk, we will first see some background on smart contracts and privacy in the world of smart contracts. I believe that you people are very familiar, maybe more familiar than me, with smart contracts, but still, we're gonna see some motivation of this work. Then we're gonna go to see a summary of our contributions, what we did in this work. Then we're gonna dig into the solution, the actual solution, the cryptographic construction that we present, that we call Jigsaw. This is gonna be a bit technical. I hope not too technical. I try to, I mean, since this is a seminar, I mean, I had to put the technical details, but I didn't want to put like the very, very, the very, very technical stuff. It's still kind of high level, so I'm gonna expect a lot of questions, at least in the technical part of the talk. And yeah, we also have benchmarks and implemented our work, so we're gonna see them. And yeah, at the end, of course, conclusions, open problems. Your feedback would be very, very, very useful. Maybe some open discussion. And yeah, as Misa said, please ask me questions throughout the talk. By the way, it's also still very early here, so it's very possible that what I'm saying does not make sense, because some of the things that I'm saying do not make sense because it's still too early for me. So yeah, please ask questions. And without further delay, I'm gonna start with the background. Okay, so the very, very basic smart contract platforms, the way that I see smart contract platforms, and I am a cryptographer, I'm not really like a blockchain person. For me, smart contract platforms are like decentralized computing machines in which we have some programs. These programs are called smart contracts. They are stored in the blockchain. And then these programs that we call smart contracts are taking some input data. This input data come from the blockchain, are stored in the blockchain. So they take this input data, they are executed, they give output data, and then the execution of this program, of this smart contract, is happening throughout many different machines around the world, and they give the same. They're supposed to give the same output, and once this is executed and validated, it goes on chain. So on chain, roughly we have the input data. The transaction of the execution of the smart contract that goes on chain is the input data of the smart contract, the actual identifier of the smart contract, let's say the description of the smart contract in some sense, and the output data. So, by the way, to keep things simple, I like to think the smart contracts as functions. So it's more like close to my cryptographic taste to think them as functions, but in essence they are programs. But I guess throughout this talk, I'm gonna use interchangeably programs and functions. Okay, so a very important example that we're gonna use in this talk is the example of decentralized exchange. So in a decentralized exchange, for example, in a very simple decentralized exchange, we have a user that, for example, says, I have 2 Bitcoins. I want to exchange them with Ethereum in price 1 to 30. And this user sends this order, this intent to the smart contract. This is one of the input data. Then at some point in the future, another user comes and says, I have 70 Ethereum, for example, and I want to exchange them with Bitcoin in price 30 to 1. So the smart contract, this function of the decentralized exchange, is executed, sees that there is a match in the price, in the intents of the 2 users. So she outputs the corresponding results of the exchange, which is that the first user takes 60 Ethereum, and the second user takes 2 Bitcoins, and the remaining change, which is 10 Ethereum. So the input of the smart contract is essentially 2 inputs, and the output is 2 outputs per user. And the 2 outputs are, one is the result of the actual exchange, and the other is the remaining change. So the first user takes 0 Bitcoins as a change, and the first user takes 0 Bitcoin as change, and the second takes 10 Ethereum. Okay, so this is a decentralized exchange, and then everything goes on chain, like the input of the decentralized exchange and the output, plus the fact that this decentralized exchange happened. Is this clear? I mean, this is an important example, and I guess it's very simple. It should be clear. So, by the way, I cannot see you, like, if there are messages, and I mean, I can only get questions, like verbal questions. I cannot see the chat. So,
yeah. No worries, Dimitris. I will bring up the questions. If someone writes something in the chat, I'll just see you.
Awesome. Many thanks. Okay. But, okay, of course, there's an obvious privacy leakage there, because, as I said, everything goes on chain, right? So the type of the computation, the function, and the data of the computation, the input and the output data, everything goes on chain. So this is something that is publicly available to everyone, even if this party does not participate at all the blockchain. It's something that we can download and see what happened. And of course, this is a big privacy leakage, and it is a very well understood issue in the area. So it's not just an academic issue, something that cryptographers are worried about. We have actually seen real-world de-anonymization attacks. From the academic side, we have hundreds or maybe thousands. I don't know, of papers that study the issue. They provide real de-anonymization attacks. So in some cases, they can really find who is the person behind the transaction. And there are even companies in the industry world that are focused on providing analytics on the transaction graph of blockchains. So this is really a big issue, very well understood and very well studied. And again, we have cases where they have actually found in the real world the person that was behind the transaction. So yeah, and this is a credit to Sanjam. I'm not using social media that much. I'm not using X or Blue Sky. I don't know exactly what it is, but yeah, this is a recent tweet probably that references Vitaly Buterin, who says that it is important actually for as global to focus on 4 key categories of privacy apps, and private money, private identity, private voting, private messaging. Just saying that it seems that privacy is really an important issue in the area. Some of these applications we are gonna talk about in this talk, and yeah, so this is an important privacy problem, and of course there has been a long line of work that focuses on trying to resolve this problem, to tackle this problem, adding to add privacy in smart contracts. Essentially, we call it privacy preserving smart contracts. So I have categorized these works according to the tool that they are using. I guess the most widely known, the most popular ones are ZK Snark based. I think the first work was Hawk in 2016, and then we have Zexy that is very, very popular. It's also deployed in the real world. Then we have very Zexy, ZK, Zapper. These are other academic works in the area. Then other people have tried to bring multi-party computation in combination, of course, with some amount of ZK snarks in order to add privacy. Works like ZK Hawk, VZK Hawk, or the more recent Eagle. There are some other works that have experimented with fully homomorphic encryption, FHC, like Z-Star or Smart FHC. In my mind, these works are still mostly in the theoretical side. FHC is not really, in my opinion, it's not really there for deployment. And the problem, at least in Smart FHC, is that they really need to use multi-key fully homomorphic encryption, which is much, much worse than even the fully homomorphic encryption. So I would say that these works kind of provide theoretical results. And then there is another line of work like Arbitrum or Ekiden that tries to entirely avoid using cryptography. So they are using trusted execution environments. These are essentially, this is trusted hardware. So they try to add privacy for smart contracts without using cryptography, but instead using trusted hardware. So, of course, myself, I'm a cryptographer. I always prefer the cryptographic solutions that are based on mathematical problems or cryptographic assumptions rather than trusted hardware. So yeah, of course, this work is not gonna assume trusted hardware. And okay, as an honorable mention, there are works that tackle specific applications, like of course Zerocash, extremely popular. There's corresponding cryptocurrency Zcash that focuses just on payments. So that's a very specific smart contract in some sense. And this line of work is even bigger. I'm sure that I have missed a lot of works in this space for specific applications. So in this work Jigsaw, we're gonna use MPC combined with the ZK snarks. Okay, so in a very, very high level, the way that all of these ZK snark-based privacy-preserving smart contract solutions work is very, very simple. So the main idea is very, very simple, is that these works are shielding somehow the smart contract execution with a ZK snark. So instead of running the smart contract execution in the plane, you run the smart contract execution locally inside the ZK snark. And then in the blockchain, instead of storing the smart contract execution, you are storing the corresponding zero-knowledge snark of correct computation of the smart contract, which is, of course, since it is zero-knowledge, it is private. It doesn't say anything about the execution of the smart contract, and it hides the corresponding information about the smart contract execution. This is the very rough idea of ZK snark-based, of all the ZK snark-based solutions out there. Some of the solutions like Hawk or Zapper do not focus on hiding the actual smart contract, the type of the smart contract. So this means that in the blockchain, you would know what type of smart contract was executed, but you will not know the data of the smart contract, the input and the output. And or Zexi, for example, focuses on hiding even the smart contract, the type of the smart contract, the description of the smart contract. So in Zexi, everything is private. Okay, so now going to our work. The main motivation of our work is the following: that in this ZK snark-based solution, so even if this ZK snark that goes on chain is fully private and of course does not say anything about the data of the clients on chain, we should still in this scenario we still have a party off chain that collects all the data of the smart contract, executes the smart contract, and then executes the zero-knowledge prover for the smart contract in order to generate the proof or the transaction and post it on chain. So this means that there is a single entity off-chain that collects all the data, that should know all the data and execute a smart contract. And the question is, who is exactly this party that can have access to all the data? Is it reasonable to consider that there is a single party that off-chain has access to all of this data of the clients? So we considered this an off-chain privacy leak. And of course, in some cases it is reasonable to assume that we have this trusted, let's say, central entity. For example, in cases where all the data of the smart contract come from a single user. So if, for example, I want to execute a smart contract on my data, of course, I can then compute the ZK snark proof myself, and there is no actual privacy leakage because all the data are mined, but this is not really the case in more modern, more recent applications, essentially in the decentralized finance space. As for example, in the decentralized exchange that I mentioned, then there you have, for example, two clients with their intents, and then the party that receives the orders of the client has very powerful front-running capabilities, because this party gets to know the information, the intents of the client before this smart contract, before the decentralized exchange is executed and goes on chain. So this is clearly a clear front-running advantage of this entity. And this is even more problematic in auctions or in voting. We cannot really think of a trusted entity that knows all the votes of all the clients, for example. So I guess the motivation of our work is this off-chain privacy leak. So going to our actual contributions, we introduce this notion that we call Doubly Private Smart Contracts. This is a definitional framework that of privacy in smart contracts that enjoys both the traditional on-chain and the off-chain privacy that we define. We construct a doubly private smart contract protocol that we call Jigsaw. This is a cryptographic construction that we're going to see in a few minutes. We implemented and benchmarked our solution, and some numbers like looking ahead. So everything works kind of nice. So for example, the off-chain time to compute this a transaction is always going to be in meaningful applications more than 3 seconds off-chain. And this is going to be 40 to 50 times faster than the naive solution. I'm going to describe what the baseline, the naive solution is. And of course, in the paper, we also describe some applications. I'm going to briefly mention them as well. Okay, so about doubly private smart contracts. So in this work, we assume that between the clients and the blockchain, we assume that there is something that we envision that we call as a privacy provider service. So we envision it as follows, that this is a cluster of servers. These are multiple parties that are there just to provide privacy for the system. And the clients are sending their data in a privacy-preserving manner to this service. This service takes the data, executes a smart contract somehow in a privacy-preserving manner, and posts the transaction. And the important properties that we want from this is that first, integrity should hold, even if all the servers of this service are malicious. So even if every server is malicious and they collude, then they cannot provide a malformed transaction. So integrity of the blockchain should not be compromised. This means that these servers have nothing to do with the validators of the blockchain. They are completely independent parties. Another important property that we demand is fire and forget, what we call fire and forget, which is basically that the clients should send their data once and then they can completely go offline. This means that we do not want back and forths between clients and servers. Everything should be in one shot. Anonymity is a traditional anonymity property that we know that the transaction that is posted on chain should say nothing about the identity of the clients. And the crucial property that we introduce is this off-chain privacy, which says that as long as one of the servers is honest, is not colluding with the rest of the servers. So as long as we have one honest server, then the servers, none of the servers learns anything about the data of the clients. So we can afford what we call like one out of like all but one malicious servers. So this is the model of Doubly Private Smart Contracts. I think it's pretty straightforward, but still, if there is any question, I guess it's a good time to ask, because this is a model is kind of important.
I might ask a small question if people are thinking for now. So you said that the security assumption for privacy is the n-1 dishonest party. So as long as one party is honest, the privacy will be preserved. Okay.
Yeah,
and do you realistically assume that this server network is small? So do you like, I'm maybe jumping a bit ahead, but I'm thinking, is it a secret sharing type of thing? So how many parties do you envision in the middle? Like how big is this network in the middle?
I mean, we envision it to be like relatively small.
Mm-hmm.
I guess it depends on the multi-party computation protocol that, of course, that you're gonna use. I guess this is not gonna scale for millions of servers, or for maybe for 1,000. I'm not sure. Maybe for small 1,000 would scale, but realistically, we think that these servers are not gonna be very large. So we actually implement this, I don't remember now, for 3 or 5 servers, but this is just for our benchmarks. It would work for hundreds, but I'm sure that it would affect the performance because of latency problems and communication and everything. I think we envision this service like to have a small amount of servers.
Mm-hmm. Okay, this makes sense. It's not like a threshold setting; it's like n-1 setting. We can return to this later. I feel like it is useful to think of this as a small subcommittees selected from like a bigger committees of participants, because the guarantee is quite high. So probably there is some kind of probabilistic argument that can be made about choosing one honest party from a big committee of like validators on chain with good probability.
The way that we think about it is that, okay, you're probably thinking that some of the validators can do this work. The way that we think about it, of course, this is only in our minds. We have no intention of deploying that ourselves. But the way that we think about it is that these are like independent parties that are gonna get paid just for providing privacy. So it doesn't have to be like that you're gonna choose like at random some of the validators, if that's what you are at least in theory. I don't know how one may think of implementing this. These are things that these are deployment considerations that we definitely we don't have a clear solution. So yeah, I mean, for this, let's say for this talk and for this work, we just say, let's assume that there are these privacy provider servers. So, okay, is it okay to, can I go on?
No other questions in the chat, so yeah.
Cool. Okay. Again, let's say philosophically in an abstract way, the way that what we do in this work is to add yet another layer of privacy. So for on-chain privacy, prior works have used ZK snarks to shield the smart contract execution. So we add yet another layer of privacy where we add NPC over ZK snarks in order to get off-chain privacy. So this is a very abstract way of thinking of what we do in this work. Probably it took very long, but I think that now it's the time to actually see the how our actual protocol works, Jigsaw. Okay, and this is going to be technical, so you should please ask me questions because some of the slides are going to be very technical and very dense. Okay, so again, from a bird's eye view, Jigsaw can be thought of as an outsourcing mechanism in a privacy-preserving manner of a zk-SNARK computation. So basically, the clients have some data and they want to, in a privacy-preserving manner, compute a zk-SNARK proof, but they don't want to do it themselves because this would be just a mess. I mean, we don't even want the clients to do so much work on stay online, and that's why they outsource this zk-SNARK computation to these privacy providers. So the clients are secret sharing their data, they're sending the corresponding data to the servers execute a multi-party computation and compute the transaction. This transaction goes on chain. This is basically, for this transaction, we rely on the now traditional Zcash and Zexi architecture. So the transaction is a zk-SNARK based transaction. And but instead of having a single entity to compute the zk-SNARK, we have a cluster of servers. The idea is very simple. Okay, I'm gonna spend some minutes to remind you. I don't know how familiar everyone is with the architecture of Zcash or the corresponding, let's say, the follow-up work that is for smart contracts, Zexi. So the main data structures are the following. The fundamental unit of the blockchain in Zexi is something that we call the record. The record should be thought of as a generalization of a coin. And amongst other things, the information that this record contains is, of course, the address public key, the payload, which is the actual data of the record. For example, if this is referring to if this is a coin, if this is referring to values, then the payload is going to contain the value and the token of the record. And it also contains something that we call the nullifier. And the way that it goes is that once this record is generated, a commitment on the data of the record is generated. So a hiding commitment of the data of the record is generated and it is posted on chain. Then the state of the blockchain is basically a root of a Merkle tree of all the commitments of the records. So we have some active records that are not yet spent, and they don't go as they are on chain because we want to hide the data of the records. So the hiding commitments of these records go on chain, and the Merkle tree root is the state of all these commitments. So then when a transaction consists of, and then the transaction consists of all the commitments of the newly generated coins, plus once a record is spent, we actually post instead of posting the same commitment of the record, we want, for unleakability, we want the commitment and the information of a coin that when it is generated and when it is spent. We don't want any linking between this information because we really want this to be unleakable for privacy, for anonymity. So when a record is spent, something that we call the nullifier is getting published. And this nullifier is actually a pseudo-random function computation of some information of the record. So when a record is generated, the commitment goes on chain. When a record is spent, the PRF, the nullifier, is going on chain. It's very clear, of course, from the properties of the PRF. Nobody can say that, nobody can link this nullifier with a prior commitment, and this is how we get anonymity. This is again ZCAS and the corresponding Jigsaw architecture. So yeah, the transaction consists of all the nullifiers that were spent, all the commitments, the new commitments that were generated for the transaction, the description of, at least in our architecture, the description of the smart contract, plus, of course, a ZK snark proof that the smart contract was executed correctly. So what does this ZK snark proof say? It says that all the nullifiers are valid to be spent. For example, their corresponding commitment is part of the Merkle tree. The newly generated commitments are well formed, plus that the smart contract was executed correctly. The logic of the smart contract is not violated. All of these things should be proven inside a ZK snark, and the corresponding proof goes to the transaction. Okay, so by the way, yeah, as a note is that Jigsaw also has a function. In our work, we decided not to hide the function, not to hide the type of the smart contract that is executed. We could still, like cryptographically, we could still design Jigsaw so that it hides the function, but it would add the overheads in the performance. We think that it is reasonable to think that hiding the data is still reasonable. It's a reasonable compromise between performance and privacy. Okay, so again, going to our example of decentralized exchange, there is one record from the first user. The record contains in the payload the 2 and the Bitcoin. The record of the other user contains the 70 and the Ethereum. And this is sent together with the intents, with the orders of the clients to the servers, and then the servers somehow should output the newly generated records, 2 records per client, and of course the transaction that, amongst other things, contains this ZK snark proof. So this is somehow what I described before for the specific example that we said for the decentralized exchange. Okay. There are some things that do not look very good in this example that I described. So some challenges that we have to overcome. There is one thing that is kind of should be bugging you somehow, is that these servers, these records are outputted by the servers, which means that these servers somehow are generating the corresponding secret keys of these records. It's like let's say, think about the mass coins as UTXOs for now. So if the servers are generating these coins, then for the clients to get the secret keys of these coins, they should communicate back with the servers, which means that there should be a back and forth between the servers, and this will be problematic. Plus, we really don't want the servers to know the secret keys, because we said that for integrity, the servers should be considered that this should work even if all servers are malicious. So the solution for that is pretty simple. We use the homomorphic property to the commitments. So the clients are pre-generating some dummy records. So the first client is generating the one record, two records with a uniformly random payload, and then this means that since these records are generated, then the client knows the corresponding secret key, and then the only thing that should change in this record is the payload. So this means that we can use the homomorphic property. And the servers homomorphically update these dummy records to the actual actual records that should be outputted in the transaction. So I'm generating some records with a uniformly random payload, and the servers homomorphically update the commitments of this record with the actual delta that should be posted on chain. Does it make sense? Is it something that is clear, or should I? Okay, so
Dimitris, just a 13-minute check.
Sorry?
Keep track of time.
Oh yeah. Sure. So the second, and I guess most important challenge is how do we actually compute this MPC for the ZK snark. So this is something that is kind of intuitively it should be something really expensive to compute an MPC for the ZK snark computation. So for that, there was this work by Ozdemir and Bonnet in 2022, a very elegant work that introduces collaborative ZK snarks that is essentially doing this exactly thing that we are looking for, to compute an efficient multi-party computation for a ZK snark prover. So in this scenario, there is no server that knows the full witness. Each server knows only a portion of the witness. For example, just a part of the witness or a share of the witness. And they involve in an MPC protocol, and at the end, they provide the ZK snark proof for the full witness. So even if nobody knows the full witness, this MPC posts a ZK snark proof for the full witness, and nobody actually learns the part of the witnesses of the other servers. So the elegant thing with this collaborative ZK snarks is that the actual construction adds very little overheads to the actual ZK snark computation. It's only about 2 or 3 times worse than the actual ZK snark computation. It does not add the full overhead that an MPC would normally add to this process. So it's very efficient, but even if it's very efficient, when we try to apply these collaborative ZK snarks for smart contracts, it's going to be prohibitively expensive, even this more efficient collaborative ZK snark solution. And the problem with collaborative ZK snark is that first, each server's computation is proportional to the full witness and not to the small witness that they are holding. But the most important problem is the communication overhead, where essentially in traditional ZK snarks, the only thing that is important, the only metric that typically, the most important metric at least that we care about is the number of gates. This is the metric that dominates the performance of a traditional ZK snark computation. In collaborative ZK snarks, for each depth of for each layer of multiplication gates, the servers should actually communicate. So this means that for each layer of multiplications, we have some latency, and this means that the multiplication depth is really of essence, because this communication cost can be sometimes even worse than the computation cost So imagine this having, I don't know, hundreds of rounds. This means hundreds of communication between the servers, hundreds of rounds of communication between the servers. So this can be this. It is something interesting that in collaborative ZK-SNARK, this metric plays a very, very important role, the multiplication depth of the circuit. So, for example, Poseidon hash is a very, very well-engineered hash function for conventional ZK-SNARKs, but it's not as suitable for collaborative ZK-SNARKs, because even if it has a very small amount of gates, it has a high multiplication depth, the corresponding circuit of Poseidon hash, which means that for collaborative ZK-SNARKs and we have like very, very, very somehow generous, very generous estimations for a collaborative ZK-SNARK. For a Merkle tree opening, it would take more than 2 minutes in order to compute a Merkle tree opening and a corresponding transaction. So this would be really prohibitive. It would not be practical for like to get these collaborative ZK-SNARKs as they are off the shelf and apply them for smart contracts. And okay, now it gets even more technical. So let's see. Let's get a closer look on the actual relation that the ZK-SNARK is computing for a transaction. So there are, as we said before, there are mainly 3 things. One thing is that I want to prove that the nullifier that is spent is the nullifier of the record that is spent is a correct PRF, is the output of a correct PRF of some value of the record, and this value of the record is committed in the corresponding commitment, and this corresponding commitment is part of the Merkle tree, and again that the address public key is correctly generated. All of this cryptographic information should be proven inside the ZK-SNARK. The second thing is that the new commitments that I generate are well formed. And of course, the third thing is that the logic of the smart contract is not violated, that the smart contract was executed correctly. For example, that the decentralized exchange on the payloads of these records is correct. So this really contains a lot of cryptography. It's too much crypto to put to a collaborative ZK-SNARK. And all of these operations, the PRFs, the commitments, and especially the Merkle tree verification, have very high multiplication depth. So the core observation of Jigsaw, our core technique, is that basically the bulk of the work in this relation just only includes local data. So essentially the first 2 parts of the relation of this ZK-SNARK computation are essentially local. It's something that the clients themselves already know. It's about their coins, and the coins, these dummy coins that they generate. So it's about their old coins and the new coins that they generated. So it's actually something that the users know locally. And the only thing inside this relation that uses information for multiple users is this smart contract execution. So the main idea is to let each client compute a local ZK-SNARK for the maximum part of the relation that they can. So each client computes a local ZK-SNARK for the data. And then the servers compute the collaborative ZK-SNARK only for the very small amount of computation that is left. So this is the very, very the core idea of Jigsaw. It's basically like this observation of splitting of the relation between local and collaborative ZK snarks. So now the way that it goes is that each user is locally generating a ZK snark for the information of the records, sends this to the servers, and the servers are computing, again, a collaborative ZK snark only for the smart contract execution. And okay, so the way that we put it is that, again, the first user is computing all the things about her coin, like the nullifier, the commitment, Merkle tree verification, the well-formedness of the new commitments, and so on and so forth. The second client, the same, and the third proof is only about the decentralized exchange, is only about the smart contract execution plus these deltas that I talked about before. So I guess some people in the audience would already see that the way that I have put it until now, it's not secure, because the final transaction contains all the local proofs and the collaborative ZK snark proof. And the way that I have put it until now, it's not secure because we have no way of somehow linking the three proofs. So we really want to make sure that the data of the first client is the ZK snark is computed over the same data as the ZK snark that is computed from the MPC. So for this, we resort to this commit and prove ZK snarks. And I saw here somewhere in the audience. So this is a work by Campanelli, Fiorel, and Querol from 2019. So basically, we say that we really want these ZK snarks to be commit and prove, in the sense that the data that is shared between the snarks should actually absolutely be committed and opened inside the snark. So we need to really open this linking commitment between the three proofs. And this is a nice application of commit and prove snarks, because for example, in Lego snark, in the work by Campanelli et al., these proofs were computed by the same prover, and it was split only for efficiency. Now, in our case, it's important that these proofs are computed by completely different entities. So we really need commit and prove snarks, because these proofs are actually proven by different parties. So it's not that there is a single party that knows all of this information. So this is how the relations for the final proofs look like. And the summary is that now, for the local ZK snark proofs, for the client side, this is where all the cryptography happens. The Merkle tree inclusions, the commitment openings, the PRFs, all the cryptography goes to the local snark. The local ZK snark computation is, of course, much better than the collaborative ZK snark in terms of technology, in terms of performance. So this is where we want all the expensive operations to go. This is no more expensive than a ZK snark, than a Zcash transaction. It's very similar in terms of costs for the local clients. And then from the server side, the collaborative ZK snark only contains the execution of the smart contract, which in some cases is extremely simple, as for example in decentralized exchange or auctions, and plus a few field operations to compute these deltas that I mentioned before. So this is all in all. This is Jigsaw altogether. There are some more details that maybe I don't want to really go into. For example, we need some signatures of knowledge because we want to bind the proof that the user sent to the very specific intent of smart contract. So we don't want the servers to take the local proofs of the clients and execute them with respect to a different smart contract. So we really want to bind the intent of the user with the proof, the local proof that they are sending. For this, we are using signatures of knowledge. I guess I can refer more for this to the paper. We also have some proofs, what we call the proofs of correct secret sharing. We don't want, this is because we don't want the clients to somehow sabotage the execution of the transaction. We really want the servers to know that their shares are correctly computed. So yeah, at the end, this is how Jigsaw looks like altogether. At the end, the transaction contains all the proofs, these commit and prove commitments, these signatures of correct, these signatures of knowledge, and the deltas for the coins. So I guess it's a good time to stop for questions. I'm gonna continue to the applications and implementation very quickly, but I guess it's a good time to ask questions if you have for the actual protocol, for the actual construction.
I would say, Dimitris, it would be nice if you could maybe slowly wrap up with the rest, and then we can have a bit of time for questions.
Awesome. Yeah. I'm almost done. Okay. So the applications that we describe in the paper that are very efficient to happen inside Jigsaw are, at least the ones that we have benchmarked, are atomic swaps or trading, sealed bid auctions, lotteries, voting, whatever has simple representation, simple to prove representation as a smart contract. It's very, very efficient, very easy to do in Jigsaw. So these are the applications that we describe in the paper. For the implementation, very quickly, for the local snark, we use TurboPlonk. We use custom snarks for these leaking proofs, for this commit and prove framework. We use also some custom ZK snarks for correct secret sharing. Our benchmarks are on a MacBook Pro, on a laptop. They are though with multi-core implementation, multiple cores. I mean, here there's nothing really surprising. It's like, let's say 1 to 4 seconds, 1.3 to 3.6 seconds for the applications that we benchmark. Basically, we want to benchmark this to show that the local proof computation does not take long. This is not the interesting part. This is really something that was done before, for example, in Zcash or Zexi, like the local proof computation. The important part is this collaborative ZK snark. And we argue that this collaborative ZK snark is going to be very, very efficient. So it's going to be actually very practical for, at least as a first solution for this off-chain privacy. So essentially, okay, we have different experiments for atomic swaps, auctions, lotteries, and voting. Nothing goes beyond 3 seconds. So the time to compute, like the time to compute this collaborative ZK snark inside the MPC by the servers, that will never take more than 3 seconds. And for all the applications, in some cases, it's extremely efficient, like less than a second. And okay, again, this is for 3 servers. I guess, I mean, this is really it's really somehow a proof of concept, then implementation proof of concept benchmarks. So we have done it for 3 servers. Of course, it can be done for more. There's nothing stopping us to do it for more. Probably the performance would be affected. But at least for 3 servers, these numbers are at least 40 to 50 times faster than using generic collaborative ZK snarks. So the baseline solution is to take collaborative ZK snarks and put all everything like the full relation there inside the collaborative ZK snark. This would take again at least a couple of minutes or 3 minutes. So this, like Jigsaw, this let's say this splitting method, like our protocol is at least 40 to 50 times faster. And I guess this is all I have to say. Okay, for verification, it's just, I mean, it's the typical verification. For verification, it's the typical gas cost that it takes to verify a Plonk proof, plus a little bit more for these linking proofs. But in any case, yeah, this is all I have to say. For the conclusions is that basically, I think the main moral of our work is that collaborative ZK snarks can be efficient. It's not something that should be considered completely inefficient. It's something that can be practical. And in terms of privacy, our main message is that the more elaborate the applications become, the more elaborate the privacy challenges become. So new ideas and new frameworks should be introduced for privacy once the applications are more delicate. So off-chain privacy is essential. That's what we want to say in this work, that yeah, collaborative ZK snarks have the potential for real-world deployment. It's something that can be practical. And then for future work, we have some, I mean, technical ideas. For the most part, we are cryptographers, so we would like to incorporate recursion to aggregate proofs in the transaction. We would like to explore function hiding, doubly private smart contracts with function hiding. And of course, we would like to see better multi-party computation protocols for these privacy providers. So special purpose multi-party computation for specific applications, for example, or guaranteed output delivery. These are things that we haven't thought. We haven't thought that much yet. It would be great, for future work. So this is all I have to say. Thanks for your time.
Thanks a lot.
Thank you so much. Thank you so much for having me.